Okay, so we'll start the program with an introduction to constraint programming, renamed constraint solving here on the slide. So I'm Professor Thias Guns, and again, once more, a warm welcome to everybody. So what does constraint solving, what does constraint programming do? It's a family of techniques for solving combinatorial optimization problems. And these range, for example, from vehicle routing, scheduling, packing, and many other types of combinatorial optimization problems that industry and society wants to solve. So the main paradigm that we follow in this is a model plus solve paradigm. And in this model plus solve paradigm, at the model, of course, some of you are already in the field of constraint solving, so you know this, but let me just make sure everybody is on the same line here. So the model consists of decision variables, constraints, and objective function. And then for the solving, you can use a number of state-of-the-art solvers that we will see, and then have these nicely visualized results, for example. Okay, so the current combinatorial optimization practice, actually, where does this model come from? This is an important question. And if you're just, as a researcher, if you're just creating models to solve, then it's just you, right, that is writing these things. But if we look at more realistic type of problems, it's important to keep in mind that these models are typically written by an optimization expert, who in turn is in contact with domain experts, who in turn has a bunch of other stakeholders that they are talking to, and that all have expectations towards the solutions that come out. And it's in the context of this bigger framework that often machine learning has a role to play. And so a big research trend nowadays is indeed that integration of machine learning into constraint solving. And so you have the model, you have the solver. And so bluntly, you could say the question is, can we learn it instead? But in practice, we can see that there's two big groups, two different types of research that's being done here. One is with respect to the model, and there the question is, can we actually learn part of the problem specification? Can we learn part of the model? And for example, the objective function or other coefficients. And the other big category is actually learning to solve, or more specifically, learning to solve faster. Can we get solutions faster, better solutions, or even approximate solutions? And so those are the two big trends. And here at the summer school, you will actually see a range of topics that fall either in the learning to model or in the learning to solve. So let's have a quick highlight look at that. So in the learning to model, so one challenge could be, for example, if we're just giving examples of solutions and non-solutions, can we actually learn the entire constraint specification? So, or even if you have a textual description of a problem, can you actually learn what that set of decision variables and constraints could be? So that's one type of learning, constraint acquisition. Dimos is giving a talk on Friday. Another big category, which we call predict then optimize problems, or in terms of learning techniques, decision-focused learning, is where you have a lot of contextual data and you want to be able to learn the cost coefficients, for example, energy prices or other ways of balancing off, doing trade-offs in your objective. You want to learn them from data, and you want to do this learning as good as possible. So we'll have Elias giving a talk about predicting problems, and also in Nando's talk and the Michele's talk, this will feature a bit. Another part is that sometimes you actually have machine learning predictions that are done, but these predictions, of course, it's by an approximate model, a neural network, for example, so they don't satisfy constraints. So what you might want to do is you want to take that input, and then you want to make sure that these predictions are used in a way that certain constraints are satisfied. And so in the lab session, you will work a bit with this. Hendrik might touch upon it, and I think Nando will also touch on that. And then there's many other forms of integrations, for example, machine learning-based stochastic optimization, and much, much, much more, also beyond this summer school, obviously. So that's that first big family of techniques where machine learning is used to learn part of the problem specification. And then that second big family of techniques is methods to learn to solve faster. And for example, if you have, any solver has multiple parameters, and so parameter tuning, automatic algorithm configuration, and so forth, using machine learning to predict what the best configuration is. This will be taught by Lars, so he will share a lecture on that topic. Sometimes you actually might have a good reason to want to try to predict the solutions directly and use those in some kind of bigger pipeline. There's many ways this is called. Learning optimization proxies is one of them. Perhaps Nando will touch on that. And then there's other ways. For example, if you go deeper into the solving techniques, you might want to use machine learning to learn to make branching decisions or to learn heuristic values. So this will be Quentin will touch on it, and we'll talk about that in Waterkool as well. And then, of course, if you're going to learn to branch, if you're going to learn how to make decisions, you might as well also do that learning with reinforcement learning. So reinforcement learning doing search. And again, Quentin will touch on that as well as Yingxiang. All right, so that's the big frame of this summer school topic, a topic that we are very excited about, a topic, as I said, that is pretty new, and for which we got a very nice set of speakers that are going to share all of that with you. And so again, to make sure everybody is on the same page in terms of constraint solving, I will explain the principles of constraint solving, and I plan to do this in a bit of a hands-on way with the CPMPy library that we are developing at our lab. So let's look at some examples. And the first example, the first problem that you might encounter here in Belgium is the fritkot problem. Okay, so a fritkot, that is a place where you can get Belgian fries. That's the main thing you can get there, but you can also get like some meats that are baked and so forth. And so Belgian fries, and you can get them in huge quantities. Like you just eat lots of fries. And so you can do this if you want to have a cheap dinner, but you can also do this if you're enjoying the terrace, the Oude Markt, you've been having some Belgian beers, we'll get to that. And then in the evening, okay, maybe a late night snack. So imagine that you're with some summer school colleagues, and it's already a bit later in the evening, and you want to get one big pack of fries to share, but now the question is, what sauces are you going to put on those fries? And because the sauces, that's like part of the charm, part of the taste. And then mayonnaise and ketchup, that one most of you, you can get everywhere. Curry ketchup, I don't know how common it is. But we also have some sauces that apparently are more local to Belgium. So Andalous is one. I don't know how common it is, but no, not common. Oh, good. So and samurai. So those are a bit more spicy. I can very much recommend you to try them. We actually had a postdoc from Chile, and his son told him, "Oh, make sure to bring 3 bottles of samurai." So he actually, when he was going back to Chile, he actually brought bottles of that kind of sauce. So I can recommend those, but they're a bit more spicy. And so tastes will differ between different kind of people. So the question is really, if you want a pack of fries to share, which sauces should you put on them so that everybody's wishes are satisfied? All right, now as a proper computer scientist, I thought maybe I should actually write a program about that. So let's have a look. Okay. So I collected from a bunch of friends, I collected their sauce preferences. Okay, Nora, my wife, she says, well, I want either mayonnaise or ketchup. And then Leander, a colleague, he said, well, I don't want samurai or maybe mayonnaise. And so if there's samurai, there should be mayonnaise. That's what this actually means, right? And so everybody kind of like shares their wish. And then the question is, what combination should we now try? Okay, so let's try to just combine all of the sauces. Let's just see if we can put everything on top. And then it seems we cannot add all of the sauces on the fries because, for example, Benjamin said that you can't have Andalous or curry ketchup and samurai. And I agree. You can't just have all of those 3. Okay, that's too much. Okay, so this is clearly not a solution. So what else can we do? Maybe we leave out the samurai. Ah, no, because look, and he was my PhD promoter. He said, okay, no, I mean, you cannot have, you have either not have mayonnaise or you have samurai. And so you're probably going to spend a lot of time trying to find that solution. So how can we do better? Of course, if only there was a solving technique to find a solution to this. And obviously there is, as you have seen, these are all clauses. So each of the preferences are written, so the preferences are written in conjunctive normal form, meaning that they're all disjunctions. So a set solver can actually very efficiently solve this problem. And what would it do? Well, one of the tricks that it does, it's not going to try all exponential number of combinations, that would be very stupid, is to actually look at your constraints. And if you look at the constraints, then what you see is Celine, she has only one preference, and that is that there shouldn't be any samurai sauce on the fries. So I can very much recommend you to try it. She tried it, and she says, no, it's too spicy for me. Okay, so that means that the only solution that there is, of course, cannot have anu samurai. Okay, so we know we have to put samurai to false. And if we do that, and we look at what happens to the clauses, so we can enumerate samurai everywhere, then at this point, Luke's only way to make his preference satisfied is so to have not any mayonnaise in it. And then if we actually enforce that, then we see that Nora's preferences indicate that we have to have ketchup. And so just by looking at this clause database, we were able to eliminate 3 out of the 5 choices. So we reduced from 2 to the 5th number of options to 2 to the 2 number of options. At this point, there's nothing more that you can derive. Well, there is if you pay a lot of attention, but in the simplest form, there is not. So let's just try. No, no, no. Okay, done. So the solution is we should have ketchup and Andalus, which is indeed a very balanced choice, if you want my personal opinion. Okay, all right. So this was, of course, an introduction to set and set solving. And so what these set solvers do, and their input has to be in conjunctive normal form, so it has to be a list of clauses, where every clause is a disjunction between literals. And then a set solver, conceptually, these are very well-engineered systems, but if I just give you a bit the high-level view, and so they have a CNF store, where you store all of that, and then they have a number of routines that they run on it. For example, this unit propagation, looking at which clauses has only one literal remaining. There's also techniques like pure literals. If a certain literal only appears positively, for example, if there's nobody that doesn't want ketchup, and there's a few people that want ketchup, then you know you can just set it to true. It will only make some people happy, and it will not hurt the other ones. And then many, many, many more in-processing techniques, many more things that are done on this CNF store, until nothing can be propagated anymore. So, and then at that point, the search will start, and in set solvers, modern set solvers, this is conflict-driven clause learning. So a bit the highlight of that. I'm not going to explain the details. I just want to shortly touch on it. And so there will be the propagation, for example, of the unit clauses. And then this clause learning, so the search is you pick one literal and you assign to true or false, and there's very good heuristics to do that, and you can also learn these heuristics. And so one of the classic heuristics is VSITs. So you will make a choice, but if it leads to a failure, then these set solvers, because everything is clauses, what they can do is they can do a type of clause learning, so they can look at what the conflict caused exactly and build a new constraint out of that. And so they maintain an implication graph of the assignments, and then on a conflict, they resolve the reason, and they add this as an additional clause. Right? So on every failure, an extra constraint is added, and this gives for very strong reasoning. Okay, so that's set solvers. So let's have a look at what that would look like in a system, in our case, in CPMPy. I should have a notebook here. All right. Is this a bit readable? I'll do it like this. So in CPMPy, you can create Boolean variables, for example, one Boolean variable for each of these 5 sources. Then we have each of the constraints at the preference of the friends, where you can use this for disjunction and this for negation. And then we combine all of the wishes, we add it into a model, and then if we call model.solve, it will find exactly the same solution, namely ketchup and Andaluz. Indeed, a very smart choice. All right, so in this CPMPy library, what are the solvers that are available, at least on my computer? So we have OR-tools, which is a CP SAT solver, Z3, which is an SMT SAT modular theory solver, Minizinc, which is a constraint language with lots of solvers, and then PySat. And so PySat, this is like a fantastic library by Alexei Ignatieff, so from the SAT community, and he actually interfaces to a whole lot of state-of-the-art SAT solvers that you can use. And so we integrated to PySat, and so you can use any of those. So let's say that we want to try glucose 4, Minisat 2.2, and Lingeling. Well, we just iterate over those lists, and then by giving the name to the solve command, that is the actual solver that will be used. Clearly, luckily, they all agree on the answer, and solving times are absolutely trivial. Okay, now you might wonder, we found one solution to this specific problem, but are there more solutions to this problem? Well, within CPMPy, we add some additional helper functions, some glue code mostly, things that we need in our research and that might be of use to others as well. So instead of calling just solve, you can also call solve all, and this will either use a solver's specialized mechanism to find all solutions, or it will do it manually by adding blocking clauses. But so you can just call this, and then it turns out there's only one solution. Okay, so let's go with that one. Now, if you want to do solution counting, then actually within the knowledge representation research, there's a lot of work also on model counters. And so what they do is they actually compile the constraint specification into, for example, a BDD, or in this case, a centennial decision diagram. And so we interface to the SDD, the PySDD package. And so you can also use this. So this will compile the problem and then use its very efficient model counting techniques to compute that there is indeed exactly one solution to this tiny problem. Okay, of course, you can give it a less tiny problem, and that will also still work. All right. Now there's a quote that I like very much by Peter Stuckey, one of really the core people to the constraint programming research field. And he gave this invited talk at some point called "There are no CNF problems." And the main point is that when you have a problem you want to solve, it is not yet in CNF format, right? So if you want to formulate problems and you want to formulate problems close to how you are solving them and perceiving them, you want to be able to use more expressive formalisms. For example, just standard propositional logic, where you don't just have a disjunction, but you can also use conjunctions, negations over sentences, implications, equivalences, and so forth. And so if we retake our little problem here, and so the not samurai or mayonnaise is actually Leander that was saying, okay, if there is samurai, then there should be mayonnaise to soften down a bit the spicy flavor. And so Benjamin was actually saying, I don't want the combination of these three, and so forth and so forth. All right. So within the CPMPy library, so PySat, you can't do that. You have to use some other library to translate this into CNF, and CPMPy is one of those libraries that can do that for you. So if you give this list and you say that you want to solve it with PySat, then interesting. I have to run that cell first. And so if I print this, it looks like what I just wrote, and then the library will do these transformations. Okay, it leaves the implications, but it will do those transformations for you, and this is almost in clausal format. All right. And then you can compare that, well, if you know how to undo the implications, that these are equivalent. Okay, so that's part of what constraint modeling languages do. They translate and they encode a formulation into a lower level encoding that the solver understands. All right, so within the CP community, actually, we have two themes. One theme is research specifically on solvers and how to make solvers faster, how to make them more efficient. For example, using automatic search, algorithm evaluation, but also looking at global constraints. I will say a bit more about this as well. So how to improve the solvers like OR tools, G-code, even integer linear programming solvers like Gurobi. But another part of research is really focusing on this modeling. And so in the SAT community, people assume that your problem is in CNF. In the CP community, there's actually a lot of research on assuming that you want to express your problem in a higher, more expressive language. How can we then automatically translate this to specific solvers as effectively as possible? And so many of these languages are also solver independent. Minizinc and Essence Prime are two text-based languages, and then CPMPy is a bit the new kid on the block, and it's a library. It's not a standalone language. Okay, time for another Belgian problem. Okay, and this Belgian problem starts with me giving you a bit of beer advice. I had to hold back yesterday. We were on the terrace, and then I couldn't hold back, and I was telling people, okay, you should really try triple Carmelite, this one. And so I can recommend it, but okay, I couldn't hold back. So let's start with the first one, Stella. Stella Artois, it's actually a beer that's been brewed in Leuven. It comes from Leuven. I think the bottle even used to say Leuven, but now it says Belgium. And so it's really a Leuven beer, although it's now part of AB InBev, the largest brewery in the world. So while you're here, why not have a Stella? It's a good thing to do. So the alcohol percentage is 5.2. The only thing is that it's an export product. So again, you can most probably get it in your hometown as well. So, you should have one, but it's okay if you try some other ones instead. Then we have Duvel. All right, Duvel, very nice, tasty beer, but a very high percentage, 8.5. Okay, if you drink 3, you will feel like somebody has hit you with a hammer. Maybe not on the moment itself, but later you will. Okay, so be careful, but it's famous, it's good. Yeah, so if you like beer, do try it. IPAs, we also have nice IPAs. It's a more recent trend. And so my personal favorite is the Vedette IPA. It's tastefully hoppy, so around 6%, so that's okay. And so I can recommend that one. And then the Triple Carmelite. This is, again, a strong blonde, sweeter and softer than Duvel. Okay, so I appreciate it more than Duvel. So 8.4%, it's even slightly less alcoholic. Still wouldn't drink 3. And so I can recommend this a bit more. And then there's one that is insane. Okay, so what they did was they took a delicious beer, namely Gouden Carolus, and then they added whiskey. Okay, so it's a whiskey-infused beer. It's fantastic. 11.7%. Okay, be warned. But if you find it, once I was in a bar in Leuven and they had it on tap, which is a horrible idea, but also, so if you can try it, you should. Okay, just be careful. And then finally, and some people say, I don't like beer. But in Belgium, I find it a very tricky statement to make because we have so many beers. So even if you don't like traditional beers because of the grainy taste, we also have fruit beers. And this one, Kriek Lindemans, is a sweet cherry beer. So if you don't like what you might think that beer is, you should try this one. We also call it beer, but it's not beer like you know it. Okay. So this is the very sweet one. They also have very sour ones. So be careful when you order Kriek to make sure it's the sweet one. But so try this if you think that you don't like beer. And also if you do like beer, try it and you will be surprised that it's called beer. Okay, so with this personal guide, now here comes the problem. It is the Belgian summer school problem, okay? And the Belgian summer school problem is that you just got this beautiful recommendation, but now the question is, which of these beers should you drink so that you can still pay attention tomorrow. Okay, so this is clearly an important problem to solve. So let's use CPMPy, obviously. That's why we created CPMPy, right? And a CP program has decision variables, constraints, and objective. Okay, so the decision variables, well, for each of those beers, we're just gonna have one, at most one of each, right? So a decision variable, Boolean decision variable, whether you're going to try it that evening, yes or no. And then the constraints. Okay, so what is the constraint? Well, I told you what the alcohol percentage of each of those beers is, and then for yourself, you need to know how many beers you can, how many standard beers you can drink. So Stella is 5.2. Let's say that you can drink 4 beers in an evening without suffering the day after. Then it's roughly right. Alcohol percentages don't really work that way, but let's still assume it kind of does. Okay, so you want an alcohol amount somewhat up to the amount of 4 Stellas. And then the objective is, of course, to maximize the amount of recommendation that I gave you to maximize that. And then we solve it. Okay, so let's do that. All right, the Belgian summer school problem. We're also going to use the Pandas Python library, which allows us to have this little list of data. And so it has the alcohol percentage and my recommended score for each of these beers. We put it into a nice little data frame with these columns. But then you should know that many CP solvers, they only expect integer values. So we create 2 additional columns. And so that's the ones that were on the slide. And then we create 2 additional ones where we multiply it by some factor, and then we round it. Okay, so now we have our data right here. We're going to make decision variables. 1 decision variable for every type of beer, and we gave it the name of the beer. Okay. Then you can enter the amount of normal beers that you're comfortable with drinking. In my case, that's 4. Is it? I'll have to try. Anyway, and then, okay, so the amount of alcohol of the beers that you chose. So you can just get the integer value of the alcohol from that table. So this will be that column, and then we multiply it by each of our decision variables, and then we sum that up. So this is a vectorized operation. It will work nicely. So this will be one expression, and it has to be smaller than our number of beers. And so if you look at that, it creates a weighted sum with these integer values and the corresponding decision variables, and that weighted sum has to be larger than 208. Smaller or equal. Yeah, only after your talk, eh? So for me, tonight. Yes, all right, no. So no objective yet, so we want to maximize, again, the sum of the column of those integer values together with, row column, doesn't matter in this case, the decision variables of the beers. And then we have our complete model, and so there's 1 constraint, and there's 1 objective. And then we solve it. So what is the plan for tonight? A duvel, a triple Karmeliet, and to top it off, the cherry on the cake, it's a cherry beer, a Kriek Lindemans. All right. So that's a good choice. And then you have 204 of the 208 of the capacity that you gave, with a total value of 222. Okay? That's a good choice. Now, in this case, we use the default solver, and so model.solve. The solve parameter doesn't have any arguments. So what if you have different solvers? As I said, we have a CP set solver, we have an integer linear programming solver, we have the Minisync language, we have an SMT solver, and we have exact pseudo-Boolean-like solver. I don't think I have all of them installed. No, Gurobi and Z3 I don't have installed. But so the other ones, they find exactly the same kind of solution. Again, pretty fast, obviously. Okay, so that was the Belgian summer school problem. And so this is, of course, a knapsack problem, but you know, it sounds nicer this way. So in terms of these different kind of solvers, we've seen set solvers. And so set solvers, the input that they expect are clauses and no objective. Unless you use a max set solver, then you can add a linear objective over the Boolean decision variables. A CP solver, so constraint programming solver, what does it accept as input? So it can take clauses as input, it can take linear constraints like the one that we saw, but also global constraints. I'll give some example of what that means. And in terms of objective, a linear objective or other kind of objectives you can formulate with expressions that it supports. I'll again show that later. Mixed integer programming, more accurately integer linear programming if you use CPMPy, but if you use Groby or one of the other solvers directly, you can also mix it with real valued values. And so it expects the constraints to be linear, so linear constraints, and to be the objective also to be linear. Of course, many of these solvers have extensions for quadratic programming and so forth, but that's the basic one. Okay, so let me again, just like I did for set solvers, let me just give you a flavor of how of these different solving mechanisms work. And so for set solvers, we saw unit propagation and clause learning. For CP solvers, we have constraint propagation, which is domain elimination. So what does that mean? So here's how a CP solver internally represents a problem. So first of all, it keeps each of the different constraints in the format that you post them to the solver. And so in case of set solvers, it all has to be CNF, it has to be a list of clauses. You can also give clauses to a CP solver, and it will treat it as one type of constraint, but you can also give it this linear sum, bounded linear sum, and it will treat it as a separate kind of constraint. Okay, and then also inequalities, a global constraint like all different, circuit, cumulative, and so forth. Okay, so it has, for each of those constraints, it has a mechanism, it knows how to deal with them. And what does it do? Well, the other thing it has is a domain store. And the domain store represents for every decision variable what the values, allowed values that variable can still take are. Okay, so for Boolean variables, it's just a 0 or a 1. And for other variables like this b, it can be a 0, a 1, or a 2, 0, 1. Okay, so that domain store is really at the center of it, and then the constraints will reason about their specific constraint and that domain store. And they will actually eliminate values. So does anybody see whether any of these constraints, let's say the first 3 can eliminate something from the domain store? Is there some combination of values that is impossible, that one of these constraints says no? This is impossible. Yeah? B0? Yes, exactly. So this one says that the decision variable of A, which can take values 0 and 1, and the decision variable of B, which takes values 0, 1, 2, together has to be larger than 2. But because this one can only take 0 and 1, the only way that you can be larger than 2 is if this one has to be at least a 1. And so then it's possible, 1, 1. But if this one would be 0, you know that it cannot be larger or equal than 2. Okay, so you can eliminate, and there's a propagation, that's what we call it, a propagation routine that is connected to this constraint that will check, okay, which values are absolutely impossible, and it will eliminate that. Now, if we eliminate this value, something else happens. Yeah, so I didn't explain all different yet, but all different says that each of those decision variables need to have a different value, okay? And so B and C, so B and C both have to take value 1 or 2 or 1 or 2. So the only one that can take value 0, and there's only 3 values possible, the only one that gets value is A, so we know that propagator, again, will do this type of reasoning and will derive, that means that A has to be 0, otherwise there is no solution, okay? And then this will continue. If A is 0, then again, this constraint will say, so that 1 cannot be possible, impossible, it would be too low, and so forth and so forth, all right? So this type of propagation, for CNF, it was about, for set solver, it was about the entire clause database. In constraints programming solvers, there's this domain store, and each type of constraint reasons about that domain store with its own capabilities. All right. So this propagation is done until fixed point again, and then a decision variable has to be chosen and a value has to be assigned of it. And we will see that you can also use machine learning for this in contest talk. Now, just a short highlight. So within the CP community, for let's say 5 to 10 years, we have this new family of solvers that has appeared. Lazy clause generation solvers is one name of them. CP-SAT is how ORtools calls it. It's actually a hybridization between CP solving, so this domain store with individual propagator concept, and SAT solving, namely this CNF store concept. So again, I'm not going to tell you how it really works, but the highlight is that you still have a domain store, but that domain store is also translated into Boolean decision variables, and the constraints, or at least the easy ones, they are also translated. No, that's not entirely true. Let me start again. So the domain store, there are Boolean literals corresponding to either values or bounds that are created. And then what the constraints will do is, for every constraint, it will reason at the level of that. Okay, that's a clause, that's too easy, that will just be copied straight. But this one, the constraint propagator will, for example, reason, 0 is not possible. And so what it will do is, instead of eliminating the 0, it will construct a clause that says exactly why 0 is not possible. Namely, if A is smaller than 1 and B is whatever, then B cannot have value 0. So it will not do the propagation directly on the domain store, but it will add a clause representing that elimination to the store. And the nice thing is that now we can also do clause learning at this level. Okay, and so this hybridization works really well, especially on scheduling type problems. Okay, and then the search now is actually a CDCL search, more a set search, but you know which of the variables are integer variables, for example, so you can do it even a bit smarter. All right, so that's just again a flavor, and that's what ORtools uses, that's what Chuft uses, and other lazy clause generation solvers. Okay, so I now gave a hint of how constraint programming solvers work. And because each of these constraints has their own propagation routine, that's why you can have, for example, also this all different global constraint, a multiplication constraint. There's no restriction. There's a lot less restrictions here. MIP solvers, mixed integer programming solvers, again, I'll just quickly touch on their techniques, which is using relaxation and cutting planes. And so a combinatorial optimization problem is typically NP-hard. There's an exponential number of possibilities that you need to verify in the worst case. So what it does is it relaxes this problem consisting of linear constraints over integer or mixed integer variables. It relaxes the integrality, and then what you get is a linear program. And a linear program that can be solved in polynomial time. Okay, so it solves that linear program, and that actually obtains a lower bound on what the solution could be. And then using that, it will add cuts. And so this is, of course, a relaxation. And so the integer points are the blue dots here. And the LP solution might be here at this vertex. And then what it will do is it will say, that's not an integer point. Let's see if we can shave, if we can add a constraint, if we can shave off part, if we can shave off that fractional solution, and then you get a slightly tighter formulation, and then you can do the same again and again. And then if you're very lucky, you don't have to do any branching, but typically there is still some branching that happens. At some point, you split on a variable, you divide it in the left part or the right part with respect to some threshold, and you do the same over and over and over again. All right. So I think I'm gonna skip this one. So the idea here is that it's, and because you know exactly the structure of the constraints, they're all linear constraints and objective linear, you can actually do some more global reasoning about that formulation. Just like in SAT solvers, they can do global reasoning about the list of clauses. Okay, so modeling differences. And so typically in CP, we formulate the problem at a bit of a higher level, and we can make the problem structure more explicit by having these concepts like an all different constraint or a cumulative constraint for scheduling. And so the problem formulations become a bit more high level. Mixed integer programming becomes more low level, and you typically have to be careful in the way that you formulate the problem to keep in mind that the way that you formulate it in terms of linear constraints has a good relaxation. If you have some expertise, people that are very good at this, they have this feeling about, I'll formulate it like this because the relaxation will probably be tighter. And there is actually some modeling support also for high-level concepts in some of the MIP solvers. And then the SAT solvers, so that's a very low-level encoding, just clauses. As SAT researchers, they just write their own clause generators. They typically don't use any of the higher-level libraries, but if you want to use the technology, you definitely want to do that instead of writing your own clause generators. So how should you choose between them? Well, there's no free lunch. I can give some general guidelines, but you can disagree with them as much as you want. So if it's a decision problem, it's typically a good idea to try SAT solvers first. If it's inherently Boolean, try SAT or MaxSAT first. If there's few constraints, or if it's very natural to relax, I don't know if you have intuitions for that or not, but in that case, if the objective function is really the thing guiding it, then it might be good to try integer linear programming, because its search, this LP relaxation, is guided by the objective always. So I would recommend trying mixed integer programming solvers in that case. And then if you have these suitable global constraints, or if there are these complex interactions between constraints that might be tricky to encode, then I can very much recommend to try a CP solver first. Okay. Now, the beauty of libraries like CPMPy is that you can just model it once and then try all of them. You can also look at the encodings that it produces. You might be able to come up with a better encoding. Fine, then you do that part manually, and the rest you still do automatically. Right, so that's a bit... Okay, so some final practical considerations. So you have to be careful with the model size. If you use these two, as I said, it needs to be encoded into MIP or into SAT, so they can grow very large. The solvers can also handle very large encodings, but that's still something to keep an eye out for. There's typically different ways to model a certain problem, and it might be good to try alternatives and see if that actually improves it, because these modeling choices matter. And then a final thing is that for some problems there might be symmetric solutions, meaning that although you have a decision variable, for example, a set problem, you might have some decision variables, but they can be interchanged. And in that case, if there's this symmetry in your solutions, the solver will spend a lot of effort if it doesn't recognize those symmetries automatically. So you might have to do some symmetry breaking. A topic I'm not going to touch upon, but if you find your solver to be very slow and it's about sets, so sets of elements, then you better have a look at symmetry and symmetry breaking. Read up on that. Okay. So now we've looked at the basics of how the different solvers work. So let's have a look at another very Belgian problem. I also need to watch my timing. 30 minutes, impossible, but okay. So, Sudoku. All right, I must admit this is not at all a Belgian problem. It's it is not at all, but with our lab, we do really love this problem. So it's like the toy problem of constraint programming, and we kind of embraced it, and we're going like crazy far with it. For example, we built an app called the Sudoku Assistant on your phone. You can just take a picture of a Sudoku. Great if it's Corona ones at some point again. Or for my mother-in-law, which was my inspiration. You take a picture of that Sudoku, and then it will analyze the image, it will get out the numbers, and then it will solve the Sudoku for you. All right, so it will actually do a bunch more, which I will talk about. And so we were very happy that at the AAAI 2023, we won the Best Technical Demonstration Award with this app. It's also available on the Google Play Store, so if you want to play around, please do. So what is the problem? Well, if you in the simplest approach, you can just separate it into two parts. One part is that you have the image of the Sudoku, because you have to like overlay your app. There's like a grid that you need to overlay, and then you take the picture. So we know just about where the Sudoku is. So you could cut it into 81 pieces, and then you can predict for each of the cells whether it's a number between 1 and 9, or whether it's empty. And then you can use some standard, I mean, you have to customize it a bit because of the empty instead of a 0, but this is pretty close to MNIST, right? So you can just use an existing machine learning architecture, and then you get an interpretation of the image, okay? So let's say that we have an interpretation of the image, meaning that for every cell we know whether it's empty or a number between 1 or 9, and let's assume that it's correct. Then we want to solve the Sudoku. And so this typical toy problem in which constraint program is introduced. So the rules are like this. At some point, we should give this to a language model, and it will probably show you the next slide automatically. But in this case, we're going to manually model this, so determine decision variables, constraints, no objective. All right. So there's a grid of 9 by 9 spaces, so we need a decision variable with dimension 9 by 9, integer decision variable. Each column, and so here, that is, and so we say, okay, we want a grid. Each variable can take a value between 1 and 9. Yeah. And then the dimensions of that grid is 9 by 9. Okay. So the constraints then, so it says each row needs to be filled with the numbers 1 to 9 without repeating any number within the row. And so for that, we can use this concept of an all different. And so every row needs to have, each of those variables needs to have a different value. That's what's in the rules here. So we do an all different on each of the rows, an all different on each of the columns. And then there's also these squares. Well, I'm sure you all know Sudoku. And so for each of these squares, also each of the values needs to be different. And then you call a solver. So in CPMPy, that would look like this. So we create the puzzle, integer variables with value between 1 and 9. And just like in standard NumPy, you can automatically make this into an n-dimensional array. And so we give it a shape. We say that the given is here. And that's a NumPy array, 9 by 9. And so we say that the decision variables have exactly the same shape, so it will also be a 9 by 9. And then each of the rows needs to be different. Each of the columns, for that we transpose this puzzle and then take the rows, and that's the same. And then for each of the blocks, and we can use some selectors, that's typical Python type of programming. So for each of those, again, we put an all different on what that corresponds to, what those variables are selected here with the selector. And then the final constraint is that so those that are filled in, those that are not empty or 0 in this case, they need to take their value. And then we solve it. Do I have a demo of that? No, that's fine. You will, of course not, because the lab session starts with this. It then goes into the neural networks and plenty more, of course, but one of the notebooks, the first notebook, you will see this, you will run this, and it will work all fine. All right. Good. So what is this all different constraint that is written there? And so as I said, it means that each variable in that list must have a different value. Now, what you can do is you can actually encode this in terms of much simpler constraints. And you can encode this, you can decompose it, as we say in the constraint programming literature. You can decompose it, if it has 3 arguments, into 3 inequalities. Namely, x1 has to be different from x2, x1 from x3, and x2 from x3. All right? So for n variables, you can decompose it into n times n minus 1 over 2 pairwise inequalities. But maybe you shouldn't. So would it be meaningful not to do that? And the answer is yes. It was already in the little example earlier, but here I'll show it a bit more full. So let's say that you have 4 decision variables, so you could decompose it. And then if your initial domain is that x1 can take values 1 and 2, x2 can take values 1 and 2, x3 can take values 1 to 3, and x4 can take values x2 and x1 and x4, then this decomposition will not be able to propagate anything more. This decomposition will say, okay, there is nothing else I can derive. However, if you take a more global look at this, if you reason about the fact that every variable needs to have 1 value, and so every value can only be assigned to 1 variable, then you can see that there's a special structure here, namely variables x1 and x2. They both can only take value 1 and 2. So in any solution, in any assignment that has to satisfy this constraint, 1 and 2 will be given to x1 or x2. You cannot give 1 and 2 to any of the other ones. If you give it to any of the other ones, one of those two will fall out. Okay? So by doing a bit more global reasoning about this, you can see that, okay, 1 and 2 has to go to x1 and x2. So all the other ones, we can eliminate value 1 and value 2 from their domain. This is actually exactly what you do when you solve a Sudoku. Sometimes you can see that, so it can only be in that row, so it cannot be there, so I can eliminate it. All right, so that's what a propagator can also do. So if you remove 1 and 2 from variables x3 and x4, it actually becomes a much simpler problem. So their assignment is now fixed, and you will only have to search over those two variables. Okay, so there is indeed, especially for all different and a number of other constraints, there's a good reason that you might want to not decompose it, but reason over the global structure. Yes, where's my, okay. So this all different constraint, does it only occur in puzzles? No, not at all. There's plenty of other real life problems that involve this all different concept. And one is a hotel company that contacted us. They have a number of rooms available. Requests come in, and then the question is, okay, do I have enough rooms to fit in all of the requests? And then in many cases, there's already some part of the allocation that must be fixed. Or actually, the current practice in hotels is often that as soon as requests come in, they assign that request to a certain room, and then if other requests come in, they just see if there is place. So that means that they don't reshuffle the rooms if needed. And so that company was interested, okay, what if you allow reshuffling? And furthermore, what if you allow splitting up some of the rooms? And so then it becomes a bit more of a combinatorial problem. So, no, that's another one. The room assignment problem. So in this case, we have a database with requests, the start date, the end date, and whether there's already a room assigned to them. So the customer had a specific request that we have to respect, or whether there was none assigned to them. Let me just show you some more. So if there's none assigned yet, that's none. Okay, so then basically for all those that already have a specific room, we have to say that that room must be assigned to it. And for all of the other ones, what we're basically doing is we're constructing this all different. What we're doing is we're looking not at it from a room perspective, from a day perspective. Namely, if on one day you have 5 customers that all need to have a room, then that means that you're not going to put them together, right? So these 5 requests each need to be in a separate room. So that's basically the only constraint in this problem. Well, so some are pre-assigned, and the other ones, all of the requests that overlap, these need to be in a different room. And then for the entire period, they have to be in the same room. So it's just all different constraints, and you can use a solver to solve it. And then because in CPMPy it's in Python, so that means that you can use some nice visualizations. So in this case, we use the Plotly Express, and then we have this nice little planning. And we show that in room 4, there will be this request, and then this request, and then this request, and so forth, and so forth. Okay, so that was a toy example. We can do it on a larger instance with 503 rooms. It computes a solution in 1.6 seconds if we use this all different constraint. But now, let's not use the all different constraint. I have to zoom in a bit again. And so in CPMPy, we have this transformation called decompose globals. And so what we're going to do is we're going to decompose each of the globals in that constraint, and because some solvers don't support all different, so that's what we activated here. We're going to use exactly OR tools again, which has all different, but we're going to decompose them, and then we're going to solve it again with the decomposed constraints. So let's see. It was 8 seconds yesterday night. Let's hope it is now as well. Okay, 6 seconds, all right. So exactly the same solver. This one is able to reason about these all different at the global level. This one is not, and so it's a lot slower. Okay. just a little example. All right. Yeah, and then we can visualize, of course, the result again. Okay. All right. Yeah, that was a backup slide. So in CP, we have these global constraints, and we saw an example of all different, but also if you want to do array access into other decision variables or into arrays, so where the x is a decision variable, for example, yeah, there's plenty of examples, but then that's also an element global constraint, so the decomposition of element can be a bit tricky for set and for MIP. Well, for set it's even more tricky, but for MIP, so in that case, it might be good to use a CP solver. And also in scheduling, there's this cumulative global constraint that can do disjunctive reasoning that could be worth using. Okay, whoa. Okay. So sometimes we know that these global constraints, that they do more pruning, okay? And then it's definitely worth using them, but even if they don't do more pruning, sometimes we have very data-rich problems, and it might still make sense to group them into a global constraint and to write a propagator for it, simply because you can use more optimized data structures, right? So these are the two reasons that you might want to explore these global constraints. Okay, so how I showed you a bit that we can do this decomposition. So what does CPMPy actually do, and why is this important? And so just 3 slides on the design. And so CPMPy aims to be a thin layer on top of fantastic SAT, CPE, SMT, and so forth solvers. And it wants to be a thin layer, but the layer has grown a bit, but it wants to be a thin layer. And the central concept is that of an expression. And so when you have CPMPy code, you create expressions by using these sums and these ands and these ors and so forth. And so you have an expression tree for the constraints and for the objective. And at this point, there is no rewriting yet. It just takes your expressions, builds an expression tree, and that's it. At the other end of the spectrum are very specific solvers, like a SAT solver, which only expects clauses as input, or the Gurobi, a MIP solver, or an ILP solver that expects only linear sums. And so in CPMPy, if you open these files, then it expects that there is a one-to-one mapping between the expressions that it receives and what the solver supports. Okay, that's the design decision here. So this one can be anything. This can be only those that can be one-to-one translated. So that leaves only the hardest part, the middle, namely doing these transformations, doing these encodings. And I'm not going to go into the details, but this is what the pipeline currently looks like. So it's basically a chain of transformations depending on the type of input that solver accepts. And so if you use a CP language like Minizinc, then it probably accepts all or almost all, in our case, global constraints. So it just needs to decompose those global constraints that it doesn't support, and then you can give this to the Minizinc language and you're done. Also, SMT has set modulo theories. It supports nested expressions, so you don't need to decompose these nested expressions. All you need to do is decompose the global constraints, and that's something CP specific, so SMT doesn't have that. So you just decompose the globals, and then you leave all of the nested expressions. You give that to, in this case, set3, and it will do that. In case of the knowledge compiler, also knowledge compiler can join and disjoin subtrees, so it can handle nested expressions only over Boolean decision variables, but so you can also take the FOSS line here. And for the other ones, we have to do more common stuff. We have to push down negation. We have to flatten it into a list of constraints, and that's what you get a CNF for if you only have Boolean variables. Or we continue. We have to handle reification a bit better. Then you have a CP solver, and then we have this. If you want to use a MIP solver, there's one more thing to do, pretty tricky one actually, to linearize each of the remaining expressions, and then you can give that to a MIP solver. All right. So that's really that middle part, and that's, I think, the most difficult part of CPMPy, and that's the part that we're trying to get right, and that gives you the convenience. And these are the encodings, the transformations. Okay, and so we only interface to Python APIs. A solver can accept whatever it wants, and so it can If it supports assumption variables, something I haven't explained yet, that's fine, we will support it as well. If it's incremental, then you can call it incrementally and it will reuse the state that it has, but if it doesn't, that's also fine. And it has its own solver parameters, you can have direct access and you can use all of those as well. Yep. Okay, so more Belgian problems. Do I still have some time for more Belgian problems? A little bit. Okay. Let's say that you're a PhD student in Thias's lab, and you are so kind to propose to take the visitors of the summer school on a tour in the city, right? So you decide which stops you want to visit, and now the question is, well, you don't want to make them, walk too much, right? So you want to find the shortest tour that visits each highlight exactly once and returns to the starting point. We're actually not returning to the starting point, but I was trying to make it sound like a TSP. So yeah, let's assume that we will return to the starting point, which we will not. Okay, and so the traveling salesman problem. That's the Leuven city tour problem, I mean the LCT problem. Okay, so the locations. So you will visit this evening, if you join the walk, which you should, the lecture room, that's a starting point. The Ladeuzeplein, the one from the picture, the town hall, Oudemarkt, and so forth and so forth. So these are the GPS locations of those places. Because we're in Python, we can again use these fantastic libraries, such as, what is PX? Plotly Express, the mat with the mapbox layer. So it will show these points on your map, and we're here now, by the way. Okay. We compute the distances. I didn't interface into Google's API, so we're just going to use the straight line distances instead of the road distances. But if you have a Google account, you can actually hook it up to the Google Maps API and get the actual distances. So these are the flight distances. So the variables are, for each place that you want to visit, still called a city here, you have one integer variable, and that variable, the value will be the order, so at which number of stop, no, it's not that. What am I saying? So the value will be what the index of the next stop is, all right? So if x0 has value 1, it means that when you're at stop number 0, you will go to stop number 1. Okay, that's the encoding. And voila. And then the constraints. So in constraint programming, it's actually very simple. There's a global constraint called circuit, and that will exactly enforce this, that in your array, at a certain index, you have a certain value, and that value, that will be the next stop. And this will be in such a way that you can make a circuit between those values. Okay? Oh yeah, I didn't run the notebook yet. Okay. And then the objective is, of course, well, that's just so it's the sum for the distance matrix from location of that index to the next location at that index. All right, and then if you solve it, you get a solution, which you can decode as such. Wow, that's a very boring solution. I didn't notice that yesterday. I should have switched the order to make it look more, but okay. And then that's the tour that you get. Ah, yeah, because of course I was looking at the map when okay, let's reorder it. Where is there? Okay, less boring solution. But of course, exactly the same tour. Now, some of you might like to walk a lot, so instead of computing the shortest tour, what we can also do is we can compute the longest tour, right? Instead of minimize the travel distance, we will just maximize the travel distance. So if you want, you can take this tour, which will be the longest tour you can do for these points. Yeah, that's the longest, yeah. But we will have a short and a long tour, but it's not going to be this one. Okay. Okay, so that was the Seveling Trailsman problem. So in CP, we have this circuit global constraint. We also have a decomposition. If you're using a MIP solver, there's actually better encodings, MTZ, for example. The tricky part is to avoid the disconnected components, but okay. All right, and then I was going to show some more demos, job shop scheduling, and so forth, but I'm going to skip over that. Now, so far, it's just been about traditional model plus solve. That means that you model the problem in terms of constraints and objective function, and then you call the solver and you're done. But more and more what we see is that we go beyond that, and we go through a more interactive procedure in which you have a model, you call the solver, but based on that, you change the constraint specification, you call it again and again and again, and so forth and so forth. And so the whole point is that in the past 5-10 years, what we see is that the way that people use solvers is not just like that, but solvers are typically used in an integration in a wider context. And for example, you want to have these fancy visualizations like the maps, or you want to use machine learning predictions. That's what we will do a lot in this summer school. Maybe you also want the models or the solving strategies to be explainable. So you want to ask questions about, is this the optimal solution? What are the alternatives? And you might need some master subproblem tile algorithms or interactive solving and so forth. And so what we see is that the border between the model plus solve and the integration is disappearing, and that's also why there's a larger need to do that more tightly. Okay, so in the CP community, there's this quote from Eugene Freuder, one of the early founders of the field, who says that the holy grail is that the user specifies the problem and the solver solves this. And so this was 1997. I think this was true in 1997, but I think today, in 2027, or at least 2023, I think we already reached that point. And so these languages, Minisync and SM Prime, I think they allow you to do this, but the real needs are now in supporting these more kind of interactive solving. And of course, we've built CPMPy exactly for that. So you can do incremental repeated solving. For example, the hotel room problem that you saw, the actual hotel doesn't have all of the requests at once, right? It has some requests, and then it gets one more request. And the question is, can I fit this one in? So if you solve the problem from scratch every time, each time with one more room, then this is the kind of computation behavior that you get. However, if you use an incremental solver, and so in this case, I think it's probably Gurobi. If you solve the problem for n assignments, and then you add one more, and it still has all of its state of what it used to solve the n ones, and it just needs to add one more, then it can do this much more efficiently. And so it looks flat. It's not zero, obviously. It's non-zero, but still, this incremental time is much slower. So MIP solvers, they support incrementality out of the box. Set solvers, they also support incrementality if you use assumption variables, something that can be used to toggle on and off certain constraints. CP solvers, CP set can do a bit of it, and SMT solvers are also incremental. And so if you use these solvers, you will get that benefit. Another thing you might want is to get multiple solutions. I've already showed you this solve all built-in, but you can also maybe want to add your own blocking clauses to it. And so while the solution returns true, you would add another constraint to the model, and if you solve it again, this will be with that additional constraint included. And so this type of incrementality, all of the system as a whole, make sure that this is handled correctly. I don't think I have time to show you the nice demo of Marco, but so one thing that you could do, for example, is to enumerate all non-dominated solutions. A very simple approach to that is the disjunctive method. As you call the solver, you get a solution, and you output the objective values, and then you say that the next solution, one of the objectives has to be better than the solution that you just got. Okay, so that's the constraint that you add. One of those has to have now, if it's a minimization problem, has to be better than the value that it had so far. You add that constraint, you compute, and it will find another non-dominated solution, and then more, and then more, and more. You still have to do a backward part as well. That's a technical detail, but at least this will get you, this will solve the hard part of these non-dominated solutions. And because of the incrementality, this automatically works. Combinations of solvers, I'm not showing that. Implicit hitting set algorithms is something that we need a lot. And so the red part is a MIP solver, the blue part is a CP solver, and you can just use them in the same code base, so there's very little glue code, and this has made, we're putting so much effort into making good glue code that it takes less effort to do the other parts. And then, of course, the integration with the machine learning libraries, and I will just highlight this a little bit because that's what the lab session this afternoon will be about. And so I told you before that you can treat the two problems separately, but if you have a classifier with a 95% accuracy over here, then actually 85% of the time, one of the 81 cells will probably have a mistake, and so in 85% of the time, you do not find a solution. The solver simply says unsat because of an error, one little error that creates an inconsistency. So in the lab session, you will learn to do better. You will, and so if you look at why this is happening, is that the predictions themselves take the argmax for each individual cell. Okay, that's what we do. And if the answer is false, then that one of those argmaxes is wrong. One of those individual interpretations is wrong. So let's not make that decision up front. Yeah, so these are the probabilities. So it could be empty, it could be 1, it could be 2. Let's reason over all of those probabilities instead of choosing the argmax for every cell individually. And that will mean that the solver can choose the next most likely interpretation. So we're going to use the solver to compute the most likely assignment to each of the cells such that the constraint is satisfied. Okay, that's what you're going to do. You will have more time in the lab session. Don't worry. I know this is going. This is a bit abstract, but so that's what you will do in the lab session. And we're not just taking the two separately, but we're taking the whole distribution, and then we're going to reason over that distribution. And it works better. Voila. But you will do that yourself. Okay. Yeah. So I think one other aspect that's important is that in the model and solve paradigm, you kind of assume that once you have formulated your problem, the solution is the solution and it should be the way it should be. But more and more we see that solvers are used as part of a larger framework, not just a larger technical pipeline, but also the kind of solutions that you return to users. And for example, in vehicle routing, that's actually people that drive the vehicles around. And so the tours that are given to them actually impact the quality and the joy of their job. And that should also be taken into account. And that's also a big push for more explainable solving techniques and for being able to, for example, learn preferences and integrate preferences and so forth. And so I'll close off with this bigger picture view that we have. And so currently you have a user, model, and solve. But more and more, and you will see many of these techniques here, we're actually learning part of that input from data, from contextual data. This could be preferences, this could be better price estimates, this could be volumes, demands, and so forth. And I believe that in the next years, at least in our lab, we're working more also on making the solver explain to the user why it came up with that solution. And I think this holy grail, the new holy grail, at least for us, is to maybe build a system where we can have some stateful interaction between user and between solver. And so we have a large European project exactly about that. That also gives us the opportunity to develop CPMPI and to organize this summer school. Okay, I won't explain the explanations, but so I've talked to you about the changing role of model plus solve. I talked to you about how CPMPI is able to encode to very different types of solvers. very little bit about how each of these solvers work, and the rest is, of course, to be continued, namely different ways that now learning can be integrated with that modeling and with that solving. So, thank you very much. All right, I think I spent too much time on the beer part. So we'll have a coffee break in a minute. If there's still a question that, yeah, Elias?
So for the routing example,
yes.
You mentioned, for example, the MTZ formulation.
Yes.
But in practice, nobody uses that. Because that's a weak formulation, the relaxation.
There are stronger formulations, yes.
So you will use column generation and so on. So I'm wondering, for example, for routing as a whole,
Yes.
the state of the art is branch and cut and try.
Yes, I agree.
Would we need to write basically map?
No, so yeah.
Solver which uses that layer to interface with CPMPI?
No, column generation is out of scope. So in column generation, you have to integrate with the MIP solver in a more intricate manner. Namely, you need to solve the subproblem, and then you need to compute a next cut, the next column to add, and then add it and call that again. So that is not what this library is made for.
Part of the solving, it's not part of the modeling. The modeling is more high-level.
I disagree. Is if you're implementing a column generation method, you are actually there's no automatic. Well, there is from the Germans, but.
From modeling perspective, I want to visit these cities with this many vehicles with this capacity.
Yes.
So technically, CPMPI as a modeling layer should be able to take that and potentially pass it to the
So
solver.
I know of a research lab in Germany that tried to do automatic column generation, but it's super tricky. You need to analyze your matrix. You need to find the structure that allows you to add these cuts. So I don't know of any method that can take a model and that can automatically do a column generation based of that. That's not what you mean? Okay, well, it's not our ambition in any case. Yeah. So it's true that the kind of routing problems that you get, if you're going to use a decomposition, they should be reasonably small. In OR tools, you have a multi-circuit global constraint, so it implements all of that. Well, it doesn't do column generation, but it implements it for you, and that one is more scalable. Yeah. So the solver OR tools themselves chose to have a global constraint that ensures that it's connected with efficient methods. Yeah, but I only know OR tools that did that. Yeah.